Har vi något ljud? Nu har vi ljud. Start stream, start rec. Now. Ja, men det verkar inte vilja dra igång själva. Nu står den bara och rullar. Ja, now borde funka. All right. I think we are live now. Right, I will be checking Slack for the chat, so use the Slack channel to communicate with me. If someone on campus has the Slack channel up and going, you can wave a little bit if I miss to check it. All right. Go to screen. So today we will be doing a kind of like a fast introduction to the subject and then focus a little bit on domain modeling, since that's the focus for the first workshop. And as I said before, get the book, check the lectures and stuff like that. But anyway, let's get started. So let's see if I can find my mouse pointer. So the first question I actually usually ask students on this course is, what do you think that you will do when you come to work in like 2 or 3 years? What would you like to do? For most parts, many people like coding, so programming is one answer I get. Answers you get is also planning, having meetings and stuff like that. But basically, I hope you like programming, because that's why you are here. So I hope that you will do a lot of programming when you arrive at your first workplace. But there are some steps before that. So how do you know what to program? You cannot just randomly show up and work and start typing if statements and stuff like that. You need know what to do. And you need to know how to do it, and then you can do it, and finally we check it. So this is a very basic development process. Before doing something, you need to know what to do, you need to know how to do it, you do it, and then you check that you have done it correctly. Basically, that's the little loop that we have in software development. And with the fancier names, I don't know if you remember anything from 1DV600, but something about requirements and analysis describes what should be done. We have design that describes to some level how it should be done. When we do stuff, we implement, we code, we make database tables and stuff like that. And when we check, we call that testing. So this course, of course, focused then on analysis and design. In 1DV600, you worked some with requirements, and you worked a little bit with design and implementation also. This course focused more on analysis and design. Sure, some implementation, not that much testing, at least not in this more formalized way that you should do testing in, but you will have other courses to cover that. So these kind of like activities are arranged in different ways with more or less emphasis in different types of development processes. So for example, to take the maybe most simple process, the waterfall model, we spend a lot of time doing requirements and analysis, a lot of time doing design, then a lot of time doing implementation, and finally a lot of time doing testing. And this kind of process can be fine if your requirements are quite stable. Maybe you're working in a domain, a problem area that's well known to you. You have done it many times before. You know basically the requirements already. Then the waterfall model can be a very efficient and effective development process. We have the iterative processes that want to kind of like do these activities in a loop. So we do some requirements, some analysis, some design, some implementation, some testing, and then we loop back and continue with some requirements, some analysis, some design, some implementation, and some testing. And we loop back again until we arrive at some good enough system that is ready for something. The agile processes emphasize having a low amount of documentation and emphasize having eye-to-eye communication instead of having documents. That surely depends on your team. If your team is spread out on different locations, written documentation will probably be needed to some degree. If you are in different time zones, if you develop with someone across the world that is actually sleeping when you are awake, then you have higher demands for documentation. We have the test-driven development, where we kind of like rearrange stuff a little bit. So to understand what we want to do, we write tests in some form, maybe automatically in code, maybe test cases, and they become more or less our requirements. And I bet you have already done this in possibly every little assignment that you have got from the university at least. However, I guess that the focus in your previous assignments has been very much towards implementation and then maybe a little bit of design. Deciding a little bit about, oh, how should I divide this problem? Should I write 2 functions, 5 functions, 1 class, 5 classes, and stuff like that. In the university, we tend to de-emphasize the requirements and analysis because that stuff is quite hard. You get more or less, this is what you're going to do. If there is confusion, there is often a lot of problems. People don't know what they're going to do, and they cannot start implementing, and then they become late and stuff like that. So we tend to have quite simple problems and quite small areas that we have in our assignments. Maybe it's when you get to kind of like projects courses, where this becomes more of an issue, maybe even than implementation. I don't know what to do. I don't really know what I should add to my system. I don't know what problem it is that I'm trying to solve. Sometimes you even work on something for a few weeks and then you realize that, oh, this is not what I want to do. I want to do something else, and then you try to switch projects after some weeks. So I think you will work mostly towards design and implementation. In this course, we will focus on analysis and design. But don't forget that understanding a problem is quite a challenge for software developers, because we are often we're not programming for ourselves. We're trying to solve a problem. For a customer, for the general public, for someone that's not us. And we need to understand their needs and wants. And it's not that easy to understand the insurance domain. How does insurance really work? How does banking really work? So problem understanding is an integral part of becoming a software developer. And my guess is that many of you will become like experts in some area. You will work for a company that does systems that does income tax stuff, or that does insurance stuff, or car sales systems, or something like that. Manufacturing, warehousing, e-commerce. So you will eventually find your area of expertise. So analysis and design, parts of kind of like any development process. You have done it, maybe not in a formal sense that you have written it down and documented it, that we will do in this course, but you have done it, because otherwise you cannot do implementation. If you don't know what to do and how to do it, you cannot do it. So that's natural. This course is also about object orientation, and this springs from the idea to kind of like view reality and view models and software as objects. We bundle up information and behavior into one entity that we call objects. This should be kind of like an analogy to a complex reality. So for example, if we take a complex object, a car, we can have many car objects, and they have different types of behaviors, and they have different types of information in them. So one car can have a lot of gasoline, another car can have a little gasoline. So we tend to view reality as some kind of objects. And a key feature to understand reality for humans is to use abstraction. Do you know what abstraction is? It's kind of like viewing stuff with no more detail than needed. For example, if you are crossing a street, you look around and you see big objects that move towards you. That's one level of abstraction. If you are at the Formula 1 race, you look at big objects that move fast, but you are really interested in who is the driver, how much fuel does he have in his tank left, what is the wear on his tires, what is the performance of the vehicle. So depending on the situation, crossing the street, I need to be aware of fast-moving objects so I can cross or not cross. More detail needed to enjoy a Formula 1 race. So different level of detail. And the trick is to add detail when we need it, but not when we don't. To support this, object orientation introduces some interesting aspects. We have this encapsulation aspect that we try to hide as much of the intricate details as possible. For example, I'm guessing that many of you have a driving license, but I'm not guessing that so many knows really how a combustion engine works. It's not really needed to understand how to drive, to know the intricate details of fuel injection. So all this complexity is bundled up. You have a common interface, you have a steering wheel, you have some levers, shifting gear, some pedals, but the real complexity is hidden from you. You don't need it, you don't see it, you're more interested in these basic behaviors that you have learned. And you can, by having this encapsulation, drive almost any car. So encapsulation, removing, hiding complexity that's not needed, and making sure that the integrity of the information in the object is kept, so that we cannot mess with it in different ways. Yes? Ooh. En vy där vi ser både dig och slides. So, mixed maybe? All right, better? Cool. To achieve this, we have two forms of hierarchies, and this also ties into how humans understand the world. We are really good at building whole part hierarchies. So a car consists of different parts: wheels, engine, gas tank, steering wheel. And we can take these parts and understand them, and we can understand the steering wheel on some other object than a car. So we understand reality by putting complex stuff together using parts, like Lego bricks, more or less. The parts in themselves can be quite simple. We build them together to form something complex. The other type of hierarchy we use is a hierarchy. So we understand much of reality by looking at stuff. Okay, this is a tree. We can go down one level of detail. This is a tree with leaves on it. We can go down further. This is a birch or something like that. So we understand reality by making these hierarchies of stuff. So we can achieve abstraction, because in everyday life, reality is infinitely complex. We need some way of filtering stuff. We need some way of removing detail when we don't need it, and adding detail when we need it. I will try to move this periodically. One key trait also of object orientation is polymorphism, the ability of an object to have special behavior. In many cases, as with the car, we are not really interested in the details. We are interested in that some kind of behavior is fulfilled, but really not interested in how. For example, I need to go to Gothenburg, and to do this I need a vehicle. And I could go to someone to just arrange a trip for me. And this trip could then be by car, it could be by train, helicopter, or something like that. I don't really care about the actual implementation of this behavior. I'm just caring about, I need to go to this place. This is kind of like polymorphism. I want some service. I don't really care how it's actually done. I'm just caring about the end result. How it's implemented, it's not really of my interest. And object orientation adds this as a primary feature to it. Basically, object orientation offers a coherent way to do the what, how, and do. So we can have objects as a primary source of analysis. We can do design with objects, and we can do implementation with objects. This is, of course, something that is nice, because if we can understand the problem using objects, we can maybe understand the design and implementation more easily by using objects also. We kind of like have the same language throughout. So, lastly, we have done analysis and design, we have done object orientation, and unified modeling language. Well, UML, it's unified and standardized. Why learn something else? I don't really see the point. When I started in 97, 98, there were a plethora of notations. and there was something called the language wars. But they got together and made a unified and standardized version of these languages. For example, I'm really glad that they settled on drawing boxes for classes. When I was a student, we had to draw clouds, and not clouds with one straight line, but with a dashed line. And that's not really easy to do, actually. The language is visual. We do visual modeling, so we kind of like put the stuff up on a screen or on a paper or on a whiteboard, and we can see the stuff visually. If you look at source code, for example, we're not really that good at text processing. It's easy to miss details in code, some comma here or a semicolon there. We are quite visual creatures, so having a visual language is indeed something that is good. It's a language, it's not a process, so the UML can be used in any type of project. It's not tied into being waterfall or iterative or something like that. Looking at the name, you can probably understand that it was deceived around the same period as the unified process, and is heavily referenced in unified process also. But it's not a process, it's a language. So you cannot develop according to the UML. You develop according to a process, and you can use UML in this process to do some visual modeling. It's more than object orientation. Some of the diagrams are clearly object-oriented, some are not. You have state machines, for example, activity diagrams, not really object-oriented. We have the object-oriented diagrams kind of like in class diagrams and in different interaction diagrams. They are quite heavily object-oriented. And for this course, then, we will focus on class diagrams and interaction diagrams because we use object orientation. So that is what you will do more of. So to conclude the first part of this lecture, a little example. This is the same example that is in the recorded lectures. I usually do this as an interactive kind of like thingy, but that will take a little bit too much time. And you can watch what happened during these sessions. Typically, it becomes a little bit too complicated. So this is kind of like geared down to the bare minimum. But we have a simple requirement. The requirement number 1, play dice game. It simply says that the dice are rolled and the result is presented. If the sum is 7, the player wins. Not that complicated of a requirement. I'm guessing all of you get an idea of actually how to implement this even in your favorite programming language. However, this example also shows that we make a lot of assumptions when we read this, probably. So if we are to start coding, maybe we codify these assumptions into our program, and later on, this is not at all what was the intention of this requirement. For example, how many dice? Doesn't say. How many sides on the dice? It doesn't say. And stuff like that. So adding some analysis to this, because you kind of like, oh, it's a 6-sided dice, of course it is. And it's 2 dice because the sum is 7, so we need 2 dice. But these are assumptions that we make, and sure, in this little example, they are innocent, but launching a space shuttle, you really don't want to make assumptions. I thought that was feet. Actually happened, and the satellite crashed. So we make this little analysis, a domain model, and we find 2 very important concepts here. We have the concept of a dice game, and we have the concepts of a dice. And when doing this, we realize, well, the dice has got to have a value. And what value do we have? We don't see anything in the requirement, so ultimately we need to go and ask, of course, but at least we have found the problem. We have decided on a value between 1 and 6. And we have also decided that the dice game rolls 2 of these dices. So we have kind of like found the problem in the requirement, but in this case we have done some decisions based on this. In reality, go back and ask someone that's supposed to know. So that's the small domain model in the examples in the lecture. It's kind of like becomes a little bit bigger, but this is the bare minimum, I think. And you can kind of like understand. If you only got this visual thingy, you can kind of like understand what this is about. Well, it's some form of dice game where a dice is rolled. You don't really know the rule of the sum. That's not really present in the domain model, but you get at least one view over this system. Do you remember the next step? Do you remember assignment number 2 from 1DV600? No, long gone and buried. We do some realization of the requirement in this form. So we do a sequence diagram. So we decide what objects are there, what messages are sent between these objects. So when doing this, this is the way he likes it in the book also. Do the use case realization first, a sequence diagram that takes the requirements, gets the input from the requirement, and then outputs the result. And to do this, objects need to collaborate, send messages to each other. Personally, I quite seldom do sequence diagrams. I use class diagrams mostly. That's the way that I learned stuff. What you like and how you do it, I don't really care, as long as you know how to do them both. Typically, I like class diagrams better. They kind of like give me more of a sense of what this is about, but it's up to you. So, in the sequence diagrams, we have objects. We have a dice game object. It gets a message play. It then uses 2 other objects of the type dice, called MD1 and MD2. It calls roll on both of these. It calls get value on both of these. And then it returns some win-lose condition. And we complement this with a design class diagram. In the design class diagram, we can see the dice game class. We can see the dice class. We can see that the dice has a member value. It's an integer. It has a value between 1 and 6, clearly inspired from the analysis. We have the operations roll and get value. On the dice game, we have the operation play. So this kind of like is the how, and now we can implement this and test it. And I think you have the implementation of this more or less at the GitHub repo of the course. So maybe you should try to make this a little bit bigger. So this is the Java implementation. I don't think it will look revolutionary different in some other programming language. But we can see here we have the dice class. Oh, I should take a look at the dice game class first. We have the dice game class. We have the play operation. It does roll on the first dice, it does roll on the second dice, and it gets the value from the first dice, it adds the value of the second dice, it compares to this magic number 7, and basically that's it. Then we have some boilerplate that's needed for this to work in Java. And we have this, it's kind of like quite interesting that we have the associations that we saw in the class diagram, MD1, MD2, two associations from dice game to dice. They are implemented as fields or member variables or what you would like to call it in your programming language, like this. And if we look at the dice, we can see something similar. We have the value, it's an integer. Would have been interesting to have a limit for it here, maybe. We have the roll, it uses some random library to do this, and we have the get value operation. So, by looking at the model over reality, we can understand much of the actual implementation. So this is one of the key benefits of object orientation, that we have this way of understanding reality that is natural to us to some degree at least. We have different steps that we take in the analysis. We focus on modeling reality. In the design model, we add software thinking to it. We devise a solution. How shall we fulfill this requirement in a software that adds technical constraints and add technical stuff to it? And then we can implement this quite straightforwardly in a programming language. Personally, I think spending a little more time here is often overlooked. As software developers, we have a tendency to jump into technical solutions a little bit too fast. So spending an hour or two on trying to understand the problem is often well spent time. However, none of these activities, I think, requirements, analysis, design, implementation, and test, are good to do for too long before jumping to something else. So spending a lot of time doing requirements before doing any analysis, design, implementation, or testing is very risky. Spending too much time on implementation without doing any design, analysis, or requirements is often ineffective, because you will implement a lot of stuff that's actually not needed or wrong or won't work in a team environment. I don't know, many of you maybe suffered a little bit towards the end of your individual projects where stuff started to become complicated. And I know that at least some people said that, all right, now that I know all this, I know how I should have done it. So I should have structured my code in some other way. I should have divided stuff in a better way. And this is what we're going to learn in this course, I hope. All right, any questions? So, good. Let's move on then. If I can get things working. So, present. We should not start at slide 6, I think. So, I think we will spend most of the rest of this time looking at domain modeling, because that's what you will be doing in your first workshop. You will focus on domain modeling and not really do any design and implementation. That will come in workshop number 2. So, first, what is a domain model? Well, it's a visual guide. We have these boxes and lines between these boxes for a specific problem, and it contains the important concepts and relations. The concepts that we saw in the dice game was dice game and dice. We had an important relation between them, the roles association. This is, of course, very small and simplistic in this example, but you can imagine a visual guide over something as complex as an insurance system or a banking system or a tax planning system, a warehouse system where items should flow as seamlessly as possible through a factory or through a warehouse. So we use the domain model to communicate and understand this problem area. So looking at a bunch of requirements, a bunch of texts, that's good. But we are visual creatures. Seeing a visual model can help us understand and put the details that are in written text into a bigger picture, so we can see how things are actually related to each other. My guess is that you will actually not start from scratch in your first projects. When you go out into work, you will come to some company and they will have something that you will start working on. Chances are that you will have no idea what this actually is and how this works. Maybe you have some kind of clue. Maybe you have used the kind of systems that they are developing to some degree, but things are often more complicated than we think under the hood. As users, we only see kind of like the steering wheel and the brake pedal. We don't see the intricate details of fuel injection. So having a visual guide over the problem area can guide you into understanding this problem area faster than just reading a bunch of texts. As you saw, we can use the domain model to find problems. So we end up with a lot of questions when doing modeling. Where should this fit? What is this? How does these two things interact? And we can take these problems back to the requirements. And we can do this quite early. So we decided upon the number of sides of the dice and the number of dice in the game. We can find improvements. We can find better ways of doing things. Maybe our customer says something. By doing this type of modeling, we can find better ways of doing things, and we can present this to our customers in a visual way that's not overly complicated. Boxes and lines, it's not really that hard. So we can find improvements also to our requirements, better ways of doing things, opportunities for better systems, for optimizing our customer, for helping our customer's customer, almost. Your computer will restart. It's funny. The IT department always has the best times of doing restarts, forced restarts of computers. We use the UML class diagrams, a small subset of the notation. We use the boxes. We can add attributes, and we have associations, and we have names for the associations, and sometimes you have the little numbers or stars at the ends, the multiplicities. So looking at requirements, the use case model and analysis model, they complement each other. They are not a carbon copy. The domain model is not a carbon copy of the requirements. Typically, requirements are very good at stating dynamic stuff. So, rules, for example. The rule of this winning condition being that the sum is over 7 was actually nothing that we saw in any of the models. Wasn't present in the analysis model, wasn't present in the design model. It was in the requirement, and it was in the implementation. Typically, requirements are easier to, it's easier to write rules in plain text, or maybe having some form of dynamic diagram for this. Behavior, actors, activities. Maybe you remember the library customer should be able to list all the books or something like that from 1DV600. Typically, requirement, actor, behavior, who can do what. For the analysis or the domain model, we focus more on information, relations that support the requirements. So what information is needed for us to be able to do the stuff that's we are supposed to do according to the requirements? This means that the analysis or domain model is more of a static view over the system. We will see some examples of this in the recorded lectures, but they interplay with each other. The requirements affect and delimit analysis because reality is quite complicated. We should focus on doing analysis on the requirements at hand, especially if we're doing iterative development. There will be some new requirements later, but we should not care so much about them at the present. And as we saw also that the domain model can refine the requirements, find problems in them, find opportunities to do better stuff than before. All right, any questions? Okay, I think then we should take a little break. And we will meet again in 15 minutes, and I will try to restart my computer because it will be forced to restart in a little while. So 15 minutes of a break.